Problem.
All right, guys, welcome back. How many of us have completed the latest homework? There's one due today. Yeah? A couple? Okay. How many of us have started the latest homework? Oh, good. Yes, I still see that your hand's not up. That's a little scary. Okay, but lucky for you, so I posted an optional assignment for this week. You know, your midterm for CS 205 is 1 week from today. It'll be in lecture, and I will write it soon, but that doesn't affect your lives at all, as long as it gets out by Monday. And it'll cover all of the material up through and including this Wednesday. So that's all of numerical linear algebra, that's understanding these error estimates and how, you know, floating point math works, and also a little bit of nonlinear stuff, although that'll be the main focus of the second half of 205A. So, you know, use this week wisely, right? Finish your problem set and then come to office hours, get help, ask questions, study all your material, do all that. But we'll come back to that in a few minutes in class because I'm going to spend some time reviewing. Are there any procedural questions before I get started? No? Once, go twice? Cool. So we have a little bit left over from our last lecture, and we don't have time to spend a whole lot of time going into the details, but the details of these two applications of the SVD are in your lecture notes, and you should take a look because it's a good sort of check on your understanding of how the singular value decomposition works. Right, so if we'll recall from last time, what we showed is we have this big pantheon of all of these different matrix factorizations that we know how to do depending on whether a matrix is square, symmetric, positive, definite, right? We have all these different properties and each one admits a different factorization. And then at the top of all of this, we have sort of one factorization to rule them all, and that's the SVD. And we learned how to compute it, right, using the eigenvectors and eigenvalues of A transpose A and AA transpose. And in the end, we get that any matrix A, be it tall, wide, square, short, singular, non-singular, whatever, can be decomposed as the product of three things. U, sigma, and V transpose. Here, U and V transpose are square matrices, and sigma is diagonal. Yes, and sigma is diagonal, period. So the big idea here is that U encodes the column space of A, V encodes the row space of A, and you can think of the action of A as first rotating, or possibly reflecting, scaling, and then rotating again. Cool? So this is a really handy factorization, but the fact that it's so general, if you'll recall, probably indicates that it's pretty tough to compute, and indeed that is the case. But the nice thing is, if we have the SVD of a matrix, there are so many different calculations that all become very trivial. And probably your next homework, which unfortunately will be after your midterm, so it is your responsibility to figure this stuff out in the meantime, we'll go through some more applications of the SVD, and I've enumerated a ton of them both in lecture and in the course notes. So two very practical ones that we didn't get to last time, we're going to talk about a little bit today. I'm going to motivate them at least, and you guys can go through the hairy analytical details at home, because we've got to keep to a pretty quick lecture pace in this class. The first is rigid alignment. So how many of you guys use an Xbox Kinect? Yeah, so remember a couple years ago, Microsoft released this new appendage for the Xbox called the Kinect. And basically what it is a 3D scanner. Right? So the idea is if you stand in front of this thing, it shines all kinds of patterns of light and this and that can sense depths from the camera as opposed to color. Right? And what you end up with is something called a point cloud, like what you see on this screen here. Right? And basically the point cloud is a big pile of points in 3 space that describes the scene that you can see in front of the camera. So a big problem when you deal with this type of 3D input is something called registration. So let's say that I want to make a 3D model of this marker, right? Now if I sit him, never mind the marker is kind of small, if I sit him down in front of the Kinect and the Kinect is sitting here, I can only expect to get points on the front half of the marker because just like you and I, the Kinect can't see the back half. So sort of a reasonable thing that people do is they take the 3D scanner and they simply walk it around the 3D object and collect a bunch of point clouds. But the problem is that each of those point clouds is in the reference frame of the 3D scanner. Right? So it's not in the reference frame of the marker, and in particular they're not aligned. Right? So if I put my marker down, I take one front, one side, one back, and one other side, and now I want to put all those together into one nice 3D point cloud of the marker. It's not as simple as just smashing them all together into one big file. Right? I've got to rotate and translate these point clouds so that they all align. Right? And so here we have two 3D scans of, well, I don't know what, but you can see that they should align and they don't when you take them, and the output of rigid alignment is just a rigid transformation of these two clouds so that they line up with one another. Right? It's a very reasonable practical problem in computer vision and graphics, and certainly with the advent of the Kinect, and now there's like a little Kinect doodad you can attach to your iPhone, this is going to become a very important problem for us to know how to solve. By the way, the problem of non-rigid alignment, like if you have a human that's deforming in front of a camera and you're trying to find the arms and all the different frames, is a very different problem, and one that is still largely unsolved. In fact, it's very close to what I do. So this is called the Procrustes problem, after a I think it's a Greek myth that's rather dark. It involves a man, trying to put people into a bed or something, and if they didn't fit, he would cut off their arms and legs to fit into the size of this bed. Historically, that's your trivia fact of the day. That's what this problem is called, and it has to do with because you want to align these point clouds in a nice rigid way, right? You can read all about this on Wikipedia. It's like a really dark story. I don't know what mathematician thought this was funny. But anyway, for us, and indeed in your lecture notes, unfortunately we don't have time in class to prove this, but they are in your notes. I worked it out in complete detail, which is good because it took me a few tries. We prove a theorem that says that, let's say that I have a bunch of points, x and y, right? And in fact, we're gonna just like when we talked about image alignment, we're going to say that the user has marked corresponding points in the two point clouds. Right? And finding corresponding points is a feature selection problem, and one that we're pretty good at in computer vision. Then the orthogonal transformation that takes you from one point cloud to another, right? The rotation that takes you from one to the other. We can't just solve using least squares because we have this funky constraint that our matrix has to be orthogonal, right? It's a very nonlinear constraint. But thankfully for us, it turns out that all you have to do is put all of your points into matrices x and y, just like we've done on the homework, multiply the two, and take the SVD, and then just remove the sigma matrix in the middle. Intuitively, this actually makes some sense, because the sigma component in your SVD is the part of the matrix that's doing all of the scaling. So if you're trying to approximate a matrix with just a rotation, then intuitively what you really want to do is get rid of the scaling factors, and it turns out this is precisely the right thing to do. And actually in several different norms. But I prove it for the Frobenius norm, because that's the easiest one in the course notes. So anyway, all of this is to say that the rigid alignment problem is a very practical thing, and it's highly non-obvious that this should be the case, but it turns out if you want to solve it, the easiest way is simply to stick all of your points into matrices and do the SVD, just like we already know how to do. So it's yet another problem that you can solve right out of the box if you have code for doing the singular value decomposition. As one kind of fun application of this, maybe I'll click this YouTube video real quick. Oops. See if this link works. There we go. Huh. In computer graphics, one important problem that we like to do is to be able to load in a three-dimensional mesh and then have your user just be able to tug on different vertices and have the mesh deform in a reasonable way. This is a good way to design a modeling tool, as you can imagine, right? So maybe I design, this is kind of a corny example. Yeah, so maybe I design my armadillo model and I want to make him dance, or I want to pull him around and deform him in different ways. One reasonable way to do this is to assign a little orthogonal transformation to each face of this triangle mesh, right? And then there's an optimization that's taking place behind the scenes as this person drags the pointer around that tries to find the as rigid as possible deformation of this surface from his initial sort of boring pose to the deformed one here. And the way that it's doing it is it's locally approximating all the little deformations of the points on the surface with orthogonal matrices. So this is actually an application of the Procrustes problem that we talked about before. And if you read through the paper, you'll see there's actually not a whole lot else to it, which is pretty neat that you can get these results. This thing is solving like, you know, thousands of SVDs per second, right? This is a thing we do a lot of. You can also see some drawbacks, right? So you see how his arm is pointing up right now? That shouldn't happen if you tug on the side. Anyway. Okay. And finally, we can return to the statistics problem I used to motivate the eigenproblems in SVD a couple lectures ago. Remember our setup here, where we have a bunch of different data points that collect age, weight, blood pressure, heart rate, whatever, of a bunch of patients in hospital, and we're trying to find correlations between different dimensions. For example, maybe a typical patient with high blood pressure also exhibits high weight, high heart rate, and high age. I'd say it's probably a pretty reasonable conclusion from a set of data points like this, sad as it may be. And we showed already that if we want to approximate this with a one-dimensional subspace, right, if we think all of our data points actually live on a line, then we can do this just using an eigenvalue transformation on our data matrix by multiplying x transpose, and finding the largest eigenvalue eigenvector pair. Remember this story was from about a week ago? But of course, not all data is one-dimensional, right? And so what we really like is some low-dimensional subspace of our data that we think we can project all of our data points onto without losing too much information. Right? So in fact, in your lecture notes, I proved for you, and again, you really should go through these proofs because it is a great application of the SVD. I know that proofs are math, and math is hard, but such is life in this class, and you really should try and understand them. But basically, what we show is that if I want to take a set of data points, right, and now I'm going to make an orthogonal matrix C, and by orthogonal here I just mean that the columns are orthonormal, I don't mean that it's necessarily full, right? And one question I could ask is, what is the best matrix C such that when I project onto his columns I lose the least amount of information? Does that sentence parse? Good. Okay. So to do that, remember our projection matrix is pretty easy to see that if C's columns are orthogonal, then C transpose times X, where X is your data matrix. This is going to project onto the columns of C, right? That's what these dot products do. Remember C transpose times X is dot products. And then you put it back into the columns of C, so you put another C there. Right? So what you're really trying to minimize is your data minus C transpose times your data over all matrices C. Right? Where you fix some number of columns, I think I said D here. Sorry, I know there are a lot of letters. Right? So I'm saying like, so maybe D is 2, meaning I want to approximate my data with a 2-dimensional subspace, and I want to do so in the Frobenius optimal way. Then it turns out the proper way to do this is you compute the SVD of your data matrix, and you just keep the things corresponding to the largest singular values. And anyway, this is the proof is in your notes. I decided not to do it in class because it does involve the trace of a matrix, and we haven't really used that in this class. So there's a little bit of homework you have to do to understand what's going on in this proof. Not much, but anyway, I highly encourage you to read it. So with that, gosh darn it. Let's go. That stuff on the side really bugs me. Okay. With that actually completes our discussion of numerical linear algebra. Congratulations, everybody, you've made it this far. You've made it through part 2 of this course, part 1 being numerics and basically applications of Lagrange multipliers. And so I thought it would be valuable, especially with your midterm coming up in a week. Again, your midterm is in a week. Start studying. I thought it would be valuable to do a little bit of review and sort of to wrap up our discussion from CS 205 so far before we dive into the depths of nonlinearity, which is a whole other thing. So right, again, your midterm is in class a week from today, and it will include this week's material. So it is not just on numerical linear algebra. It's also going to include a little bit of root finding, and potentially, depending on how quickly I talk today and Wednesday, some optimization. But not much. Okay. Right, so what have we done so far? Basically, in the first 4 weeks of CS 205A, we have analyzed to death this system of equations right here. AX equals B. We have dealt with the case where A is tall, where A is short, where A is singular, where A is invertible, where A is square, where A is symmetric, where A is positive definite. Hopefully you guys get that all of these things show up in practice and in different places. And basically your job in numerical linear algebra is to take a look at a system of equations like this to figure out what properties this matrix A has, and then to exploit them to death to get the fastest, most well-conditioned, best-behaving solver you can, right? And we have any number of tools to do this. So I thought I'd go over some kind of big ideas that we've covered so far. We started by kind of the most generic hammer that we have for solving linear systems, and that's Gaussian elimination. And the big takeaway, you might have gotten a little lost in notation, but the big takeaway here is that it is precisely the same as the Gaussian elimination or reduced row, echelon, whatever that you did in just linear algebra class by hand. Right? Where we sort of have the name of the game here is that we have certain row operations, right? We can swap rows, we can scale rows, and we can add multiples of one row to another. Right? That's the name of our game, and we're trying to take our matrix and reduce him from just some generic thing to a diagonal matrix, because diagonal matrices are really easy to solve. Right? And in particular, Gaussian elimination involves this strategy of kind of two different phases. Right? The first thing we do is a forward substitution phase. So we start with a matrix that we don't know anything about. Right? And then after we do forward substitution, we end up with a matrix where we've got zeros beneath the diagonal. Yeah? And then after backward substitution, we end up just with the diagonal matrix. Yeah? So that's the big takeaway. And now, the reason that some of this got tricky was, well, there were two things. First is this idea of pivoting, right? Your homework this week covers, I think, was it this week or last week? This week, right? Covers a little bit about how you might implement this type of Gaussian elimination in the presence of pivoting, and it's not that much of an extension of what you already have. And then the other thing that seemed to throw people off a little bit is this idea of an elimination matrix. Now, the name of the game, Gaussian elimination, again, is just to apply these simple rules. And all an elimination matrix is something that you can left multiply this guy by to carry out one of those rules, right? And elimination matrices are not a good way to implement any of these algorithms. You can, if you really want to, you can implement them as sparse matrices, but this is kind of a weird way to do it. But instead, the reason that we do this is because it's really convenience for understanding the theory and properties of factorizations and Gaussian elimination, right? And hopefully you saw in your homework, for example, when you derived this LUP factorization, right, with a permutation matrix, that by understanding these guys' elimination matrices, you can play games like refactoring them and moving, you know, flipping the order of permutations and lower triangular matrices and so on, right? This is somehow much easier notationally to do and to think about in terms of these elimination matrices, even if we don't use them for our final implementation. Yeah? Okay, from there we moved on to LU factorization. We know that most matrices admit LU factorizations, and those that don't are because of pivoting, right? And even then, you can do sort of an LUP type of factorization. The idea here is that you put all of your work into factoring A one time, and then from there on, it's far less work to solve AX equals B. Remember, just using forward and backward substitution. But all that LU factorization is doing is basically memoizing or storing the steps of Gaussian elimination so that you don't have to kind of go through the same motions every time you solve AX equals B with the same A. From there, we talked about sort of different types of special matrices, and one that comes up a lot, for instance, the normal equations. Remember the normal equations of things for least squares? Was Cholesky factorization. The idea here is that Cholesky is nothing more than LU factorization on a symmetric positive definite matrix. But what we showed is that in fact, this matrix U can be replaced by just L transpose. Now one common gotcha here, the LU factorization of a matrix might not be unique. And in fact, you can't say that if I write a symmetric positive definite guy like this, I can't say that U has to equal L transpose. Right? So this isn't an if and only if, but what it says is that any symmetric positive everything admits a Cholesky factorization. Yeah? So just a little gotcha to keep in the back of your head. What do we like Cholesky? Well, for one thing, it takes less space, and for another thing, it directly acknowledges the fact that your matrix is positive definite, which oftentimes is useful, because what you don't want is to have kind of weird numerical mistakes that, for example, take some eigenvalue of your matrix, which you know should all be positive for symmetric positive definite things, and accidentally kind of push it to a negative number. It would be a very bad thing to happen in a lot of applications. So after we considered all these factorizations for solving linear systems, we also wanted to think about just the column space of a matrix. So for example, if you solve least squares, one way to think about least squares is that you're projecting onto a column space. And because of that, we introduced this guy called the QR factorization. Now, in all cases, the matrix R is upper triangular, but like I saw, there's a little confusion on your problem set as to what this matrix Q is, and this is partly my fault for reusing old problems from 205A without realizing that they covered material in a slightly different way. But what we do know is that Q has orthogonal columns, right? And then remember I talked about how Q might be square if you used the householder strategy, but in the end, usually the QR factorization we care about, and indeed the one on your homework, and I apologize, it's my bad, should have said so explicitly, is the reduced QR factorization, where Q actually can have fewer columns if your column space is ranked efficient, right? So there were two strategies we talked about for QR factorization. Gram-Schmidt is a very easy one to kind of think about, right? You just start with a random vector in your column space, you normalize them, and then you project them out of everybody else, and then you just iterate this process. But as we learned, it was a little bit numerically unstable, so we introduced this householder guy, which just involves reflecting things, which is a much more numerically principled thing to do. And finally, why do we like QR? Well, for one thing, it allows us to carry out these squares without squaring the condition number, like what can happen if you do LU factorization of the normal equations. Yep. Then we moved on to eigenvalue problems, and we have yet another matrix factorization. This time, we can write A if it is non-defective as x inverse AX. Oh, yikes. dx, where d is diagonal, and I apologize for the typo on my slides. So here, x contains the eigenvectors, and d, which is the thing that should be between the two x's, is the diagonal of the eigenvalues, right? And we know that if A is symmetric, that in fact, x inverse is equal to x transpose, because all of our eigenvectors are orthogonal, in fact, right? This is the Spectral theorem, humongously important theorem from linear algebra, right? So again, the catch here is that not all matrices necessarily are diagonalizable if they don't have a full eigenspace, right? So if you have an n by n matrix, but he only has like one eigenvector and n is big, then you're done, right? But the one exception to that is the Spectral theorem, which is humongously important, and says basically if your matrix is symmetric or if it's Hermitian in the complex case, that life is good and you can always do this. Right? So we had a number of algorithms for actually computing these eigenvectors, and basically they all involve the same hammer, right? Which is that you take some random vector, literally a random vector, just some starting point, you just start hammering it away with the matrix A. Right? And our observation was that if we do this, we're guaranteed to get the largest eigenvector, or largest eigenvalue and eigenvector pair, right? And then what we did is we started playing all these games, like, well, if I take the inverse, then all of my eigenvalues flip, I can shift my matrix to get different eigenvalues close to 0, and so on. But basically, all of these games just involve different extensions of the power method. And this actually was our first example of an iterative scheme for solving a numerical problem, right? If we stop the power method before k equals infinity, which obviously is what we're going to do, then we're not guaranteed to have exactly an eigenvector of our matrix. But what we are guaranteed is that in the limit, as we iterate this algorithm, we get closer and closer to the eigenvector. And we proved this in class. Finally, once we had eigenvectors, we could introduce, and we did so in our last lecture, the singular value decomposition. This is the mother of all matrix decompositions, and it basically encodes almost everything else in this class. And an interesting exercise you can do is to look at the SVD and see if you can use it to derive some of the other factorizations we've talked about. But in particular, once you have the SVD, you can solve linear problems, you can find low-dimensional subspaces, you can do point cloud alignment like we just talked about. And so sort of the singular value decomposition is the heaviest hammer we know how to use, but also the most powerful. And remember that one thing you can do to make the singular value decomposition slightly easier to compute is to say, maybe I only care about the biggest or the smallest singular values for my particular application, in which case I don't need to compute the full eigenspace. Right? So that was one trick to get around that. So that's sort of our story so far, and there have been a couple themes that I think are important. For one thing, something that I've done a lot, and I've tried, because otherwise I think you tend to see expositions of numerical stuff that just look totally made up, and every time you see a new algorithm, they use a totally new ad hoc kind of thing. But I think a theme and the way that we present it in 205 is to use this variational approach. So the idea is that we write down an energy and maybe some constraints that measure what we're trying to compute, and then we look at the Lagrange multipliers of the derivative, we set it equal to 0, and we see what happens. Right? And this is just a good philosophy for life. Like whenever you have a problem in life, write an energy down that measures what you want to have happen and take its derivative, and chances are you'll find the solution. And in particular, there's one energy that I've written down on this whiteboard at least 75 times, which is this one right here. It's the least squares energy. Right? Notice I haven't, well actually I did put the square here. But you guys should, at this point, be able to do any gymnastics that I ask you to do with this expression here, and I highly recommend you review that before your midterm. Yeah? Okay. And the usual hammer that we use for solving these sorts of problems is is either taking the derivative or in the presence of constraints, we use this Lagrange multipliers trait. And you'll see in a couple lectures when we talk about constrained optimization that in fact, when we don't know anything about E other than that it is a function we want to minimize, then in fact what's going to happen is your optimization software is literally going to just write down the Lagrange multiplier system and try and solve it. So this isn't just something that you do on paper. In fact, the nice thing that's happened so far is that Lagrange multipliers have nice properties we can take advantage of. But that's not always the case, and we'll see examples where all you can do is just iteratively hammer away at these guys. In fact, I just posted notes for this the other day. Another theme so far is that you should look for special structure in your matrix. And I was going through my notes and I came up with this list of eight special structures that we've already seen in matrices, each of which can lead to their own special algorithms for solving linear systems, finding eigenstuff, and so on. And this is going to continue in the second half of 205A. In particular, things like symmetry, when your matrix is positive definite, then those two properties together imply a whole huge pile of algorithms. And in fact, when we talk about conjugate gradients, we'll see that even for iterative schemes, symmetric positive definite matrices have really nice properties. If your matrix is sparse, you might be careful with things like LU factorization because of fill, right? When you do these forward and backward substitution things, you tend to annihilate zeros, and that can be a problem. We talked about the normal equations, which comes from least squares. Again, you should please review that. Yeah. If your matrix is square, full rank, block, triangular, each of these things has its own special properties and can help you understand a linear system and formulate algorithms for solving it. So a skill that I think is probably the most important thing you can get out of 205A, and hopefully the thing that you've been really focusing on your problem sets, which by the way are different from old problem sets in this class, is to be able to take just some generic numerical problem that you run into in real life, whether it's in vision or machine learning. I think those are the two that I've drawn from the most so far, statistics and so on, right? And to look at this thing and squint at it the right way and say, actually Justin, this is just an eigenvalue problem. Or actually this is just least squares, right? And so on your homework, for example, when you did the kernel trick, when you did this thing that nobody liked with the metric learning, basically all that you're doing is you're taking a problem that looks very specific to a domain, right? That looks like some problem that just some random guy in Sequoia Hall might want to solve, but it actually just boils down to the tools that we already know how to do in CS205A, right? And that is the most important skill you can get out of this class, because honestly, implementing the power method is something that somebody else has done for you. There's like very little reason to implement this unless you're just really struggling with some weird numerical thing. If this turns out not to be the case in the future, send me a nasty email, and when I'm a professor in the University of Podunk, middle of nowhere, I will revise my version of CS205A accordingly. But we've seen a number of examples of this sort of pattern. For example, we showed that this kernel trick from machine learning really reduces to least squares. That solving differential equations or embedding graphs onto the plane corresponds to eigenvector problems. That doing metric learning, which believe it or not is a very practical problem, even though I use the word theorem in this homework, just boils down to certain matrix factorizations like the Levski, right? And that doing things like principal components analysis, point cloud alignment, and so on boils down to the SVD, right? Am I interested in having you actually code up the SVD when you get to that point? Meh. Chances are your implementation is going to be worse than the one in MATLAB. Certainly worse than anything I do is certainly going to be worse than anything in MATLAB. So once you get to the point where you have understood that you can basically set up some matrix and then find his eigenstuff or whatever, the steps beyond that are just implementation details. And since you guys are all advanced students in computer science, I have no doubt that you can code them up from there. Okay. Finally, one theme that we've seen so far is this idea of stability and conditioning. Right? So when you take an algorithms class like CS161, you spend a lot of time computing the amount of time that an algorithm takes by calculating the number of steps. Right? But when we do numerical analysis, that isn't enough. Yeah, we still have to compute the number of steps because we're still going to write code to implement these things, right? And there actually are numerical problems that are NP complete. This is a horrifying area of math, by the way. But that aside, not only do you have to do your algorithmic analysis, you also should understand the quality of output that you can expect, right? For example, if I perturb my matrices a little bit, or if I'm using finite precision math, then I have to be very careful if I have a poorly conditioned problem, because I'm going to be subject to lots of numerical drift if I make small mistakes during my calculations. right? And so we had a number of examples of how to understand, usually just by upper bounding. We don't care about the exact number for conditioning. Sort of a vague rules of thumbs to tell us how well we can expect our solution to actually hold, how well we can expect our algorithms to behave, and so on. You guys should review that. So, some advice. I debated all weekend whether I should address a particular comment that was posted on the course website. Here are my thoughts for those of you that saw this. For one thing, it is not my job to ask you to code algorithms that I covered in class because that is an obvious thing you can do at home. Cool? So if you see the LU factorization and you're like, I'm not confident that I understand all the details, then open up MATLAB and try it. Right? We're grown-ups. This is a graduate level class. So what I really want you to get out of 205 is this idea that you can take all of these different problems in the world and reduce them to numerical algorithms that we already know how to do. And if part of that process for you is actually implementing the algorithm underneath that, then you should do that by all means. But what I really want you to get out of this stuff is the process of recognizing this big different class of problems you can solve with this. So my advice to you, to put a positive spin on things, is that you should experiment in this class. Right? And if you see a factorization or a method that looks cool, then give it a try. And if you don't know why you would use one of these methods, then send me an email and I will send you 25 different applications. Yeah? Literally 25, I'll find it if that's what you want. So anyway, do some experimentation, and to encourage you to do this, because I know that your problem sets have involved a lot of math. This is numerical analysis class, you're going to just expect to do that. I added an extra problem set for this week that is completely optional. In fact, you will not get any interesting credit for it. You just get extra late days in this class, which I noticed a lot of you guys are in dire need of. Basically, all I did was list out a list of sort of function templates in MATLAB that I think you should be able to implement after the first half of 205A. And for each two that you implement correctly, you can get a free late day. Okay? Cool? Deal? All right. My other advice to you is ask for help. I know that this course is challenging and I'm not going to apologize for the amount of math that's in it, so please come talk to me if you're having trouble, come to office hours, your midterm is in a week, you got plenty of time, and we're all very patient guys here at USAT. So anyway, that concludes the first half of 205A about numerical analysis, conditioning, and so on, and from here, we're going to embark upon a much more general set of problems that I think is very important to sort of study on their own. So if there are any questions about either numerical linear algebra, how to study for the midterm, or anything before I proceed? No?
Is midterm mostly like problems in homework?
Yeah, obviously it will be considerably easier, and I will ask that your TAs verify that since my idea of easy doesn't necessarily align with all of yours.
And then the second question, would we get the format of it? Like 5 questions?
Yeah, so there'll be like probably about 7 or 8 questions. I'll let you skip one. Don't hold me to that. I reserve the right to put whatever the heck I want on this exam. Cool? Anything else? Yes.
Do we have a crib sheet?
Crib sheet. Yeah, sure. How about one double-sided sheet? I don't care that you memorize this stuff. I don't think it'll help you a whole lot anyway. Anything else? Okay, great. And you know, in general, I really do appreciate your feedback, and you should keep it coming. You may consider the means by which you share it, but we can discuss that offline. Okay. All right, and with that, we move on to nonlinear systems of equations. Come on. There we go. Now for something completely different. Not completely different, but somewhat. So the next part of CS 205A makes the following observation, which I think is probably pretty clear to most people in the room, which is that not all numerical problems can be solved with back